Hey, today we're going to continue chapter 0, so parts 5 through 8 I'm going to go over. Let me pull up the smartboard and share the screen. There we go. All right. Let's see if I can get the camera angle right here. Okay. All right, so starting with chapter 0, part 5. So this section is systems of equations and inequalities. And I got some Keanu Reeves memes for you here. All right, so first of all, there are a few methods we're going to use. The first is solving by substitution. So to solve by substitution, you're going to pick an equation, solve that equation for one of the two variables, and then plug in the expression that variable is equal to into the other equation. So let's go step by step. Step 1, we're going to solve for a variable. And I hope you can see that the second equation here is the best choice because it has a variable that has -1 as its coefficient, and that's going to make it pretty convenient for us to solve for that variable without fractions or anything. So 5x minus y equals 14. We want this to be y equals something. So first of all, I'm going to subtract 5x, and I get -y equals 14 minus 5x. And then if I multiply both sides by -1, I'll get y equals 5x minus 14. So when you multiply a binomial by -1, and it's a difference like this, a convenient way to find that is to flip the difference. So the additive inverse of a binomial is the flipping of the difference. Just a quick way to do that. Okay, so that's step 1. We got a variable to solve for. Step 2. We're going to plug that expression into the other equation for y. So we've got 2x plus 3y equals 9. And so this is going to become 2x plus 3 times 5x minus 14 equals 9. And now you see we have only one variable, so we can solve this for x. So 2x plus, distribute this 3 here. 3 times 5x is 15x minus 42 equals 9. Combine our like terms here, 17x minus 42 equals 9. Add 42 to each side. We get 17x equals 51. We divide away the 17. We get x equals 3, like so. So we have x now. So step 3 is going to be to plug x in. We back up here, y equals 5x minus 14. So if I plug in the x value, I can also find y. So y equals 15 minus 14, and y equals 1. And now we have both the x and y. We have solved our system. So system of equations is when more than one equation is true for the same variables at the same time. And to solve the system, you need to solve for all the variables. In this case, there was an x and a y. And we use the method of substitution. All right, solving by elimination. So elimination is a little different. We want to force the coefficients to match. And there's a couple different ways we can do that. but the easiest way is to pick a variable, and I'm going to pick the y variable here. So I want to make the y's match. And what I'm going to do in order to make that happen is to multiply each by the other's coefficient. So I'm going to multiply the first equation entirely by 5. And the second equation entirely by 2. And the result is going to be 5 times 1.5 is 7.5x. 5 times 2y is 10y. And then 5 times 20 is 100. 2 times 2.5 is 5x. 2 times a negative 5y is minus 10y. And then 2 times negative 25 is negative 50. Okay, so now you'll notice in the two equations we have matching y coefficients, at least their absolute value matches. So I can add those two together and they will cancel out. So once you have matching coefficients, and elimination is most effective in systems that already have matching coefficients, but you can make it work by this method as well. So I'm going to add the second equation to the first and create a new third equation that we're going to solve. And the y is going to be not present in our third equation. 7.5x plus 5x is 12.5x. 10y plus a negative 10y is 0, and that's the key. We have canceled out or eliminated the y, hence the name elimination. And 100 plus a negative 50 is 50. So 12.5x equals 50 divided by 12.5. And I get x equals 4, like so. Okay, so now we have the x, same process as before. We're going to plug that back in to get y. I know that 1.5x plus 2y equals 20. So I can pick any true equation about x and y, plug in the x value, and it'll allow me to solve for y. So 1.5 times 4 plus 2y equals 20. So 1.5 times 4 is 6, plus 2y equals 20. Subtract away the 6 here, and I get 2y equals 14. Divide away the 2, y equals 7. So once again, x, y has been solved. And this method we call elimination. So the first step is to create matching coefficients. So we did that here. The second step is to add or subtract one equation from or to the other, to cancel out and create a new third equation. And then step 3 is to solve that new third equation. And then step 4 is to plug that known equation value into any true equation and solve for the other. All right. So systems of 3 variables. So there are algebraic techniques to solve these. In fact, you can do it very much like I did the previous problem. Substitution works just fine. It just takes a very long time. So with this one, we're going to use the method of RREF, reduced row echelon form, creating an augmented matrix. So when we make our matrix, we're going to get information from the rows for each equation. So row 1 is going to come from equation 1, row 2 from equation 2, and row 3 from equation 3. And then the variables x, y, and z will be used in each column, only their coefficients, and then the number that that equation is equal to in the 4th column. So this is a 3 rows by 4 column matrix. And I have 1, 2, and 4 as the x coefficients. -2, 3, and 10 as the y coefficients. 1, -1, and -5 as the z coefficients. 15, 7, and -3 for the values they are equal to. So that defines our augmented coefficient matrix. And we're going to punch this in the calculator and use the RREF function. So I can't really get my calculator screen up here Actually, I can if I just share the whole screen. Guess I'll do that real quick. I tried sharing just the window, and that didn't work out so hot. Your entire screen. There we go. So if I use the matrix function and we want to edit A, it's already a 3 by 4, so the dimensions are good. 1, -2, 1, 15. 2, 3, let's already in here. 2, 3, -1, 7, 4, 10, -5, and -3. Okay, so that was already in place. So once the matrix is defined, go to the matrix menu again, go over to the Math tab, navigate all the way down to option B, which is RREF. Now hit the matrix button again, pick the matrix that you defined, and hit enter. So this is going to give us the reduced row echelon form, which is 8, -2, and 3 in our rightmost column, which is what we're chiefly concerned with. So what this tells us is 1x is equal to 8, 1y is equal to -2, and 1z is equal to 3. So once again, we've solved our system. Again, algebraic methods exist for 3 by 3 methods, 3 by 3 matrices, and 3 by 3 systems, but they're lengthy, they're unwieldy. It's nothing you should ever choose to do if the calculator is an option, and it always will be, even on the ACT or whatever. Okay, so here's a couple that have what I call special solutions. So when you have two equations, so these are linear, in other words, a straight line. So if you think about how two lines can intersect, so far we've had this situation.
Please use the list of 10th grade students that was emailed out and identify those who have completed the device agreement form on Scalar. If you have a student who is in need of a device and is on the list, please send it to the comments. See Mr. Ledford at this time. Students, please have a seat in the comment when you arrive. Thank you.
So far we've had this situation, which is one intersection, one solution. But there are two other situations that are possible. Two lines could be parallel and not share any points, and that would be a no solution situation. Or they can lie right on top of each other and share every point. That would be infinite solutions. So you can have one solution, you can have no solutions, or you can have infinite solutions. Okay, so in this first case, we're going to solve this using elimination. So I'm going to add the second equation to the first. So I get 0 plus 0 equals 38. So 0 equals 38. This is what's called a contradiction. And if using legitimate algebraic steps, you arrive at a contradiction, that means you have a system with no solution. So you can stop immediately when you encounter a contradiction. And say no solution. Okay, so second one. Let's use substitution in this case. That'd be a little unwieldy. Yeah, let's go ahead and do it. So 5x plus 2y equals 12. If I solve this for y, I get 2y equals 12 minus 5x. And then divide away a 2. And so y equals 12 minus 5x over 2. Now if I plug that back into the other equation, I get. All right, so we're back to this problem. So we're plugging in the expression we found that y is equal to into this second equation to create a new third equation. 20x plus 8 times 12 minus 5x over 2 equals 48. So if I distribute that 8 to the numerator, so That's 96 minus 40x, quantity over 2 equals 48. Divide each of these by 2. 20x plus 48 minus 20x equals 48. The 20x's will cancel, and I get 48 equals 48. That is what's called an identity. In other words, something that's always true. And if you encounter an identity by legitimate algebraic means, you can immediately stop and say this system has infinite solutions. All right. So here are some problems. If you want to pause this and work through these, it can help reinforce what we just talked about. So graphing inequalities, this is kind of fun. It's an exclusively graphical problem to express inequalities like this. You can do it with numbers, but it's not a good way to see the solution. So graphs are the way to go here. Okay, so let me pull up a graph. And add it to my slide here. So you first want to graph equation 1, which I'll call this one. And we note that it is less than. Now, if you have less than or greater than, you're going to graph those with a dotted line, indicating that the line is not part of the solution. If you have an inclusive inequality, less than or equal to or greater than or equal to, you're going to graph those as a solid line to indicate that it is part of the solution. So in both cases here, we'll have a dotted line. 3x minus 8. The related equation, you just change the inequality symbol to an equal sign to find the related equation. 3x minus 8. We'll graph that because the y-intercept is negative 1, 2, 3, 4, 5, 6, 7, 8. And then you go up 3 and over 1 to find the next point. Up 3 over 1, 3 over 1. Because the slope is positive 3. So there's our first line. Now, what we need to do is figure out if it's this side or this side that satisfies the inequality, because it could be either. So we're going to pick a test point in either region. It's generally a good idea to pick the origin if it's an option, and it is here because the line doesn't touch it. So if I plug in 0, 0, and I'll call this my TP test point, 0 is less than 3 times 0, which is 0, minus 8. 0 less than negative 8, that is false. So in the case of this first inequality, the test point of the origin fails. So it's not this side, meaning it has to be the other side. So I'm going to use a little highlighter here. The background's kind of interfering, but you guys get the idea. Problems are kind of fun. Apologies to anybody that's OCD if I left a spot out there. I'm trying to get a little more accurate with the line. All right, so that's the first part. Now y is greater than or equal to 3x plus 4. So positive 4 is our y-intercept for the related equation. Y equals 3x plus 4. And again, we're going to use a dotted line. 1, 2, 3, 4. Up 3 over 1, up 3 over 1. Back 1 and down 3 to find points on this side. And so dotted line. Test the origin. So that would be 0 is greater than 0 plus 4, 0 greater than 4. Once again, it's false. So the solution side does not include the origin, meaning it's the other side. We use a I suppose. So once you're finished, indicating the solution areas for the two equations. Where they overlap is your solution set. And in this case, there is no overlap and hence no solution at all, unfortunately. Matrix operations. So this is all about matrices, dimensions of a matrix. So when I have a matrix, it is an array set up in a number of rows and number of columns. So I'll have some number of rows and some number of columns, and the dimension will be the rows by the columns. So in this case, if I were to say like this, it would have 1, 2, 3 rows by 1, 2, 3, 4 columns. So the dimension of this matrix would be 3 by 4. Important to be able to find. A row matrix, and we'll just talk about these real quick. They don't happen very often. You use them when you're performing row operations typically. But a row matrix is a matrix with just one row. A column matrix is a matrix with just one column. A square matrix, the rows and columns are equal, and a zero matrix has 0 for every element. So just some terminology to be familiar with. Adding and subtracting matrices, they must have matching dimension, or the sum or difference is not valid. So they have to be exactly the same number of rows, exactly the same number of columns. Otherwise, you cannot add or subtract. So let's put some matrices up here. I'm going to define A, B, and C. Like so. So if I were to find, as an example, A plus B, I would say that has no solution, because the way I've set these up, A is a 2 by 2 and B is a 2 by 3. And so we see their dimensions don't match exactly. Even though they have the same number of rows, the number of columns differ, and so there's a dimension mismatch, and we have no solution. However, if I were to do C minus 2A, like so, this would be valid, because A is a 2 by 2 and C is a 2 by 2. And this scalar value of 2 here, I would just multiply every element by 2. So this is going to look like 1, 7, 3, negative 2, minus 2 times 1, 2, 3, 7. And so 1, 7, 3, negative 2, minus 2, 4, 6, 14. And so now you add or subtract corresponding elements. 1 minus 2 is negative 1. 7 minus 4 is 3. 3 minus 6 is negative 3. Negative 2 minus 14 is negative 16. And you probably know how to do these in your calculator, but these were so simple, easier to do them by hand. Okay, so that's adding or subtracting matrices. Scalar multiplication, you just saw. So when you have a scalar that's a number, like 2, and we're multiplying that by a matrix, so equals every element of A multiplied by 2. So when I scale a matrix, I'm going to multiply every element in that matrix by that scalar value. So that's when you multiply a matrix times a number. All right, multi-step matrix problems. So if I have a matrix, like say negative 2B plus 4A. that would be an example of a multi-step matrix problem because I have to scale them before I do the add or subtract. So it is a multi-step, and you saw an example of that earlier. So I won't do another one, but that's what we define as a multi-step matrix problem. Matrix equation. So in order to solve a system, you saw me use the RREF method, but you can also use a matrix equation. So any equation like this, if you use capital letters, that typically indicates a matrix, can be solved and used to define all kinds of problems, but it's most often used in the solving of a system. So I can solve a system with the matrix equation, and we'll go into that more in chapter 6. But for now, know that it's a technique that you can use. So here's some problems. Feel free to pause the video here and look over those if you feel like it. Chapter 0, part 7, probability and permutation. So probability is the likelihood of a thing occurring, and the permutation are the ways a thing can occur. So that's what those two words mean. Factorials. So this is an operator you may or may not have seen, but it's a number and then an exclamation mark. And what this means is that number times that number less 1 times that number less 2, and so on until you get to 2 and then 1, and then you stop. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is also, 120. So that's factorials, and they often come up in probability arguments, or to define the number of permutations in a situation. Fundamental counting principle. So the fundamental counting principle says if event A can happen in ways, and event B can happen in ways, then event A and B can happen m times n ways together. So let's just say, for the sake of argument, you're picking out an outfit, and you've got 5 shirts that you like to wear to school. So event A will be picking a shirt, and it can happen 5 ways. And let's say event B is going to be to pick a pair of pants. So if you're picking out a pair of pants, say that can happen 4 ways. So you got 4 pairs of pants you like to wear to school. And so just picking a shirt and a pair of pants, so together, those can happen 5 times 4 or 20 ways. So you'll have, from those 9 articles of clothing, 20 different outfits you could wear. So you could wear something different for 4 weeks of school days. Also, I like sub sandwiches. So I use Subway a lot here. If you think about how many different Subway subs are possible. So how many ways can you, the first thing they'll ask you is what kind of bread do you want? And I think there are 5 or 6 ways to do that. We'll just say 5 for the sake of this problem. And then they'll say, what kind of cheese do you want? And that's, I think 5 or 6 also, probably more, but again, we'll say 5 just for the sake of this problem. And then they'll ask you for the meat option. And there are a bunch of different ways to get this, because you can include or exclude certain things, and you can ask for special orders. But again, just for the sake of this problem, we'll say there's something like 20 ways to choose the meat option. Now we've got kind of a special scenario, and that is the what I'll call miscellaneous, which would be the vegetables and so on. Each of those are a binary choice. In other words, a yes or a no. So I'm going to choose lettuce, or I'm going to choose not to have lettuce. Choose tomato, choose not to have tomatoes. So that's all yeses or nos. So each of those can happen two ways, but we're going to have to raise that to the power of how many times that occurs. So all the different types of vegetables, all the different sauces, all the salt, pepper, that kind of thing. Let's just say there's something like 20 of those. So this can all happen together. 5 times 5 times 20 times 2 to the 20. And this is really a conservative estimate. So let's punch this in our calculator. 5 times 5 times 20 times 2 to the 20th power. So let's see. 524 million and change. So we'll just round to the nearest 100 million. About 500 million sandwiches are possible. So if you ate 3 a day for the rest of your life, you wouldn't even knock a dent in the number of possible sandwiches. And that goes to show the power of the fundamental counting principle. All right, so permutation versus combination. These terms are not interchangeable. They don't mean the same thing. Permutation are the ways a thing can happen where order matters.
Because at this time, if you would use the email list of 9th grade students, identify those who completed a device agreement form on Scalar. If you have one of those 9th grade students in class who needs a device, you can send them to the comments at this time. Thank you.
All right, and combination is where order is not important. And one way I remember this is combination locks are poorly named. They should be called permutation locks. But anyway. So the permutation formula looks like this. It is when you have a set of n things and you want to choose r of them. So like if you had a set of 20 students and you wanted to choose 2 of them in a way that order was important. Let's say you wanted to choose a president and a vice president of the pre-calculus class, and you had 20 students in the class. So order matters because one's going to be the president, one's going to be the vice president. And how many ways could you choose 2 people from 20? That's defined by this permutation formula. N factorial over n minus r factorial. So that looks like this. Usually it's written, now they use a little different notation here, but usually the n comes first. So that's going to be 20 factorial over 20 minus 2 factorial. And if I punch that in the calculator, it's under math and then probability. You're looking for that exclamation mark. That's a huge number, 2.4 times 10 to the 18. And then I'm going to divide that value by 18 factorial. And it comes out to be 380. Now, lucky for you guys, your TI calculators can do these without the formula. So you don't need to have the formula memorized. Let me share the whole screen and I'll demonstrate how to do that. Okay. So in a TI calculator, if I type in 20 and then I go to math and go over to the probability, look at option 2 is NPR, and then I'll put in 2, and it tells me there are 380 permutations for choosing 2 out of 20. All right, now combination formula is the same formula, but you have an r factorial in the denominator, so it adds that value, and that controls for order not being important. So in this scenario, I'm picking 2 people from a set of 20 again, but order doesn't matter. It's a 2-person committee that will share power. There's no reason for order to matter. Okay, so that would be 20 combinations of 2. So once again, 20 factorial over 2 factorial times 20 minus 2 factorial. So once again, there's a shortcut we can do. So you may have noticed a second ago that NCR is option 3. And we see there are 190 ways Now, don't think it's always exactly half of the permutations. That's just a coincidence. All right, moving on. So there are some problems. If you feel like reinforcing what we just learned, you can pause here and work through those. 0 part 8, the last section in chapter 0, measures of central tendency. So here you've got the mean, which is just the average, which is the sum of all values over the number of values. And then you've got the median, and there are two ways to find the median. So way number one, you have an odd numbered set. You just choose the middle value. If you have an even numbered set, you're going to average the two middle values. So that's median. And then finally the mode, which is the most frequent value. So when we're looking at a set of numbers and we want to understand central tendencies, in other words, where these numbers tending to be, the mean, the median, and the mode are always to measure that. And the reason why you have three is because there's a lot of different scenarios. So imagine if I were in a classroom of high school kids and I wanted to measure the average age. Well, I would be such a strong outlier, I would skew that data up to, a year or two older than the student's age in class, but it wouldn't be an accurate measure of central tendency because of that strong outlier myself skewing the data. So that's the case where the median would be a better choice. So if you have outliers that skew your data, choose the median. If the numbers all fall within a pretty reasonable range, the mean is a better choice. The mode is rarely used. Measures of spread. Okay, so when we're talking about how data is spread out, we have a couple primary things. First of all, the range, which is the highest value minus the lowest value. And we've got the standard deviation, which is a complicated formula that I'm not going to get into because it goes beyond the scope of this class. But it's a way to express the concentration about the mean. So your calculator can find this for you, and I'll show you how to do that when we get to that section. But when you have a normal curve, and all data related to human performance tends to fall on a normal curve. You remember that looks like this. And you'll have some mean that we usually express with the Greek letter mu. The way the data is clustered, and we use sigma often to indicate the standard deviation, the way the data is clustered around the mean is predictable with regards to the standard deviation. So I know that 68% of people, for example, would fall within one standard deviation of the mean. And then, let's see, that would be another 13.5%. I think it's, 95% within two standard deviations. And then only 2.5% would fall outside of those ranges. So this is really important when somebody tells you something that's unlikely. Like if somebody says, hey, I've got a 190 IQ. No, you don't, dude. It's extremely unlikely, virtually impossible. Or, hey, deadlift 1,000 pounds. No, you don't. It's too far out there, too many sigmas for that to be even remotely possible. Okay, organizing data. So we can display data in charts. You can use a pie chart. You've seen these where they indicate how much of a thing is in a certain category. You can have histograms. You can have scatter plots. So those are all ways to organize and display data. And we'll work with some of those going through this book. So here are some problems. I'm not going to assign this, but feel free to take a look at those if you're bored, and hope you have a good day.